Okay, so today we'll look at a summary of total variation that we covered last time, just to make sure we finish on it, right? And then we'll go through supervised learning, we'll start supervised learning and binary classification. So that's going to be a new topic for today. So, the way I look at this class is there'll be concepts, there's assignments, there is intuition, and there's an application. So every time we come across new material, ask these three questions. What's the concept here? Do I understand the concept? What's the application? Why are we covering this? Just that should be in the back of your mind. Okay, why are we covering SVD? What's the point, right? So we did discuss examples for it. And what's the intuition? Like, how does k-means work? How does this work? Because if you go to YouTube or any other tutorials, like you have tons of tutorials of any of these topics, right? So why are you here then? Because we're going to go a little bit more into the intuition of it, right? So people might just say, okay, if you do this, you use this library, you'll get this job done. But that doesn't give you intuition, right? So but asking why does this work? Why not use that method? Why use k-means plus plus? What is the computational complexity? Why do we care about computational complexity? So whatever, asking that why is going to give you more out of this class than anything else. So don't just settle for, okay, I think I understand this, and so ask more questions to yourself, or you can also ask in the class, right? So you can deepen your understanding. Okay. So I found a good book on machine learning concepts. Since we're covering classification, I'll refer you to this book. So you can, if you want to go a little bit more into classification, you can look at this. We'll also cover classification in depth in the next course, Advanced Introduction to Machine Learning. But in this course, we'll cover the relevant aspects that is needed for computer vision and image processing. So last class, we looked at total variation for image smoothing. This is the motivating picture. You have your original image, but you're given this, and then you want to smoothen it. And hopefully you kind of worked on this in assignment 2, and you got an experience of how the algorithm is able to smooth things. So there's many other examples you can think of, right? And you can also think of combination of things. There's noise, there's blurring. There's also something called occlusion. So it's a little bit more advanced denoising, where you occlude objects, and you kind of like maybe, instead of this, maybe here you have something like this. You have these lines, you have a pattern, maybe something is grayed out, something is, but you still want to return a cleaner version of this. So this is, you may have to do more than just total variation in that case. So there's like advanced methods to denoise images that have specific kind of occlusions and things like that. I don't think we'll cover it in this course, but I can point out some references if you're interested on this. I think there's something called low rank plus sparse decomposition for occlusions. So you can look it up, this specific phrase, low rank plus sparse. You'll find a paper on it, you'll find some references on it. So a little bit more advanced technique on how to denoise. If you notice, in total variation, we didn't use sparsity. We use the fact that the gradient is sparse. So with occlusion, which is a more complex thing, there is this low rank component that gets added that can help separate things. So I'll kind of refer you to Google this and learn more about it. So we looked at background for total variation. We covered L1, L2 norms, and what do they do? What does it look like? What's the intuition behind these norm balls? Look at this. Like, why is L1? So the key thing here, the key intuition is L1 is connected to sparsity. And this is also a good interview question. Someone says, hey, you want to do feature selection as you are doing a model, as you're doing classification? How do you do automated feature selection? And you say, okay, use L1 norm as a regularizer, and it'll kind of sparsify your features and it produces a lot of zeros. So this is the intuition, right? You get a 0 here. You're hitting the boundaries with L1, but you're not hitting the boundary with the L2. So if you optimize, if you use it as a regularizer, you add it on to your objective function, it is somehow producing solutions that have a lot of zeros. So that is sparsity, right? In our case, for total variation, it is making the gradient smooth, which is sparse, right? Smoothness is there's not much change between consecutive pixels. So L1, so this is the key intuition here. So L1 is helpful with sparsity. L2 is still useful as a regularizer. It can help prevent overfitting. So we haven't covered overfitting yet in this class, but it's a concept where you have more parameters than data. So when you have more parameters than data, then you can have multiple models that fit, right? Maybe we should just quickly cover it because we're talking about it. So what is overfitting? So let's say I have this curve here, and then maybe I have, okay, let's say I have 4 points, and you say find a curve that fits through these 4 points. Well, you can do multiple fits, right? So this is one fit. This is a linear fit. You guys agree? It's passing through most of the points closely. It's a linear fit. So it can help explain. You say, what's the value here? You say, okay, just look at this curve. This is the value. So it's able to approximate. It's able to predict. So linear regression, right? But overfitting looks something like this. You say, oh, you know what? I feel like it's like this curve. You just have 4 data points. How did you figure out it's this curve? Isn't that too much? So that's why it's overfitting. It's too much that you think is going on. And don't you see that this kind of curve, if you want to mathematically describe it, you would need many more parameters, right? It would be a polynomial of a high degree. Whereas this linear fit is polynomial of what degree? Degree 1. It's a simple linear fit. So this is a high degree polynomial. So in machine learning, one of the most basic things is to avoid overfitting, to recognize overfitting and avoid overfitting. And for that, so if let's say you've recognized overfitting and there are ways to recognize it, then these regularization terms L1, L2 can help you avoid overfitting. And between L1 and L2, you have L1 regularization that also makes things sparse. So it's saying, well, let's say you chose a 10-degree polynomial, and you're having 10 parameters to go through 4 points. Isn't that too much? So then, if you add L1 regularization, it's going to put all the higher degree parameters to be 0, because it likes to make things 0, and it's going to leave you with a linear fit. So you'll get back the original fit that you thought would be a good fit. So that's how L1, when combined with machine learning, can help make simpler models. So let's kind of summarize that here. L1 gives you sparse models, simpler models, and avoids. So you're not saying more than you should be. Overfitting is like, I think I know a lot. There's so much going on. The curve is going up and down. Really? With 4 data points? Are you sure? Right? Because maybe if you add a 5th data point, right? Maybe your 5th data point is here. So 6th is here. Then you're like, oh, now I think it's linear. So given 4 data points, you made this nice curve, but I added 2 more data points, and now you can see there's like the trend is this way, right? So now it's starting to look more linear. So that's why this is the danger of doing machine learning when you have less data and more parameters. So that's a very quick introduction to overfitting, but we'll spend more time maybe in the next lecture once. So then we spoke about norms and norm balls. So this L1 and L2 also have a geometry around it, right? So we spoke about L1 having a diagonal shape, diagonal ball, and then L2 having spherical. And we spoke about L1 as sparsity, and then we spoke about sparsity for image denoising. That brings us to TV. And then we also spoke about the gradient matrix, right? So there is like the horizontal gradient, you go this way, and then there is the vertical gradient. So you want the image to be smooth in this direction and also this direction. So that's why you take both horizontal and vertical gradients. And then the total variation is taking the horizontal and vertical gradients and applying L1 onto it. So making it sparse in the vertical and the horizontal direction. Right? So you want the image to be smooth in both directions. So that's why we have a combination of this. And there's more than one way to combine it. So you can combine it this way, or you can also combine it this way. So that gives rise to anisotropic, and so it should be isotropic. All right, so I thought to make it more concrete for you, we can probably do an in-class exercise. So let's say you have an image matrix that's given by this. Okay, if you look at the gradient, you go from left to right or top to bottom, it's not zeroing out, right? Most of the values, if you take a difference, it's not zero. Like, let's say you look at the first column and the second column, the difference is non-zero. So this image, based on the concept of the difference being zero, is not smooth. Would you agree? Just thinking of it in that way. So now we have two candidates, I1 and I2, that are somehow smooth. Maybe you use TV or you use some algorithm and you got I1 and I2. So the question is, which of these two images is a good approximation to I in terms of being close, but also in terms of being smooth? Right? We spoke about the trade-off last time. You don't want to you can make the image smooth by setting everything to zero. That's a smooth image, but there's nothing happening there and it doesn't match your original image. So you don't want to go very far away from your original image, but at the same time you want to smooth it. So let's say I1 and I2 are coming from two algorithms. The question in this in-class exercise is, which of it is a better approximation to I in terms of being close to I, but also making it more smooth? Okay. So we'll consider two metrics. I think let's make it d by, so that means you're going in this direction. Okay. So you're comparing this consecutive columns, right? You're comparing the second versus first and third versus second. So that is dy. And let's just look at dy. Let's not worry about dx for this in-class exercise to make it simple. And then you're also looking at the denoising error. So that is, let's say I hat is I1. You look at how far I and I1 are in, let's say, the Euclidean norm. So that is telling you, are you like going really far away from I? Because that's also not good. And this is telling you, are you making it smooth? So maybe you're applying this to I1 or I2. And in the second one, I hat is I1 or I2. Yeah, I is fixed because I is your original image. So, so I put it all in one place. So you have, this is your original image. And this is candidate 1. And this is candidate 2. So these are candidates for smoothing. You want to see which is better, like, is the total variation better? Which means that it is more smoother. So here TV is better means the TV is measured by dy of, let's say, I1. TV1 is a dy of I1, L1 all that. TV2 is dy of I2. Or is the denoising error better? So here it is I2 minus I1, I2 minus I. Here it is I1 minus. So you're comparing I2 minus I, the denoising versus I1 minus I, which is smaller. That means it's better. And you're looking at TV. So if TV of I1 is smaller than TV of I2, does that mean that TV is better for I1? Lower is better, right? Because that means you don't have much changes in the gradient. So in both the cases, the metric of lower is better for the purpose of denoising, being close to the image, or for the purpose of making it smooth. So what we can do is start with computing dy for both images, I1 and I2. Then look at how far I and I1 are. Look at how far I and I2 are. And that's going to help you answer these questions. Feel free to work with a partner so you can just kind of make it easier and make it more smoother for you. Okay, that sound good? Okay, so hopefully you saw that the third option makes sense, and it's because the L1 norm for the TV for I1 is smaller than L1 norm for TV for I2. So that means, I mean, just looking at it, right? You just look at I1, doesn't it look smooth, the transition, as you go from left to right? If you look at I, the transition is not smooth. So, but I and I1 are close to each other, isn't it? I mean, as close as maybe I and I2, right? So you see that these are approximations of I, but this is more smooth than that. So when you did the TV for the assignment 2, the algorithm was looking for these candidates and picked the one that has the best trade-off between the denoising error and the TV error. Right? Isn't that what you guys did? Yeah. So it's just a small illustration of it. So conceptually, this is what it looks like. Any questions on this?
What might be optimal TV ratio of the similarity versus?
Yeah, so it's a trade-off, right? So here we are just looking at, in this case, your candidates are such that one is somehow better than the other on both the metrics. But usually there's a trade-off. One might be worse on this and one might be better on that. So that's why you have a regularization parameter, lambda, and then you look at the summation of both the errors, the TV plus the error. So you look at that value and see which one has the smaller overall value for that. And that's what happened in assignment 2 is you were looking at a trade-off and the algorithm picked the one that has the best trade-off. But that trade-off is something that you set, right? Because if you change the lambda, you'll notice that you get a different solution, isn't it? If you set lambda to be really high, you'll get zeros, or you'll just get a blank image. If you set lambda to be 0, you get the original image. So the trade-off is somewhere in between. And once you pick the trade-off, then you will be able to figure out the best I1 or I2 that fits that trade-off. So you have a choice, and then the algorithm does its thing as well. Okay, so hopefully now we're clear on total variation and what it is conceptually. We worked on it in the assignment as well. So we'll move on to the next topic, which is supervised learning and classification. So far we've only looked at unsupervised, image processing, SVD, all of that. Now we're introducing labels. So now it's going to become supervised, and this is really helpful for classification. So again, let's go back to that big picture. So we were here, then we looked at dimensional reduction, we looked at clustering, we looked at data visualization, we looked at compression. So we looked at a few of these things. And now we're moving here. So and beyond. So from now on, we'll be in the realm of supervised learning. Almost every application that we'll look at from now on will fall under supervised learning. So we'll look at classification mainly. Regression, I don't think we spend as much time in computer vision, but if you want to know more about regression and other methods here, you can take the next course on advanced introduction to machine learning. We'll get the whole spectrum there. But for this course, we'll stick to classification, because that covers a lot of models that we care about in computer vision. So if you remember in the first lecture, I kind of outlined a bunch of topics in computer vision that we'll be touching upon. So let's just look at where we are right now. So we covered image processing using convolutions, image denoising, image smoothing, and image clustering. And today we start on image classification, and then we have a long way to go. Like each of these can be like 2-3 weeks. So we don't have too many weeks, but we'll try to get through as much as we can. So hopefully we get to image to text. That's my goal. But text to image maybe a little bit. But yeah, this would be a good goal to hit right to here. All right. Okay, so we spoke about classification in lecture 1 as well. The very classic example is you have different species of flower. In this case, it's subspecies of the same kind of species, like a flower, and you want to be able to differentiate these. So maybe we'll have this part of the next assignment as like a starter problem, and then we'll have a more involved image classification problem as well. So you'll see how you can do image classification based on different kinds of data. So here, in this particular problem, if you see, these are all the iris flower, right? So we're looking at iris. So iris setosa, iris versicolor, and iris virginica are 3 subspecies of iris. They look similar, but there is difference. So if you notice, this is called the petal, right? And this is the sepal. So the petal, and then you can see this petal and sepal look different in the subspecies, right? For instance, this has a wider petal, more circular petal. This has a longer, or this is a shorter petal. So some of them have a longer sepal, some of them have a shorter sepal. So just based on the length and width of petals and sepals, even without looking at an image, if you're just given that, you can classify them as this subspecies or that subspecies. So that's going to be part of your next assignment as like a starter problem. You're not looking at the image. You're just given petal and sepal lengths, and you can still be able to say that it's this subspecies or that. I mean, this is what experts do, right? You look at experts in botany, they would be like, oh, this flower looks a little bit longer here, so I think it's this subspecies. So basically, they're doing classification in their head as they're looking at these flowers. So that'll be your starter problem for the next assignment. And then there is like, we won't use any image data. Now, what if you use image data? Then you have to extract features from images. So that's a whole different ball game. That's more involved because it relies on your ability to extract features from images. So that you can use like standard features for that, maybe SIF features, or you might have to do deep learning, right? Or conv nets. So we'll get to that in a couple of lectures as well. So I just want to maybe say that classification, image classification, you have you can call it metadata or whatever. So metadata of images. So this is one type, and then the other is the actual images. So that's an example of classification for images. Classification obviously applies in other areas too. So you can have classification for emails. So not related to computer vision, but another example. So let's say you use Gmail and you have emails coming into your inbox, and your classifier says it's spam, it's not spam, it's spam, and so on, right? And it's happening in your inbox, right? You don't encounter many emails that are not spam but are in the spam folder, right? Most of your emails look well classified if you go to your inbox. Do you agree? And conversely, you don't encounter emails that are spam that end up in your not spam or in your inbox. So Gmail has gotten it down really well. It's doing really good classification on classifying emails as spam or not spam. So how is classification different from regression? How many of us have heard about regression before? Maybe in some previous class. So regression is usually like, I think we also spoke about it, in terms of PCA, look at a line of best fit, right? So whenever you see this line of best fit going through a lot of data points, that's regression. So this is linear regression. Right? So in regression, you're trying to fit a line through as many data points as possible, as closely as possible. Okay. And the target type, which is what you're trying to predict, is numeric in regression, but for classification, it's categorical, right? So here, what's the target type here? Okay. For this data point, I predict this. For this data point, I predict this. So these are numeric, right? They're not like a category. But for classification, as in this example, it's either spam or not spam. So that's categorical. You have two categories. Or you can have multi-class, you can have multiple categories. Maybe it's spam, not spam, maybe you want to archive it. Maybe there's like other labels you can apply, but it's still categorical. So one is continuous, and this is continuous. And the other is discrete. So that is one difference between classification and regression. And in terms of a picture, you can see how the picture also looks a little bit different. In regression, you're having a line going through all the data points, whereas in classification, you have a line separating two different clusters. So it's not going through the data points, it's actually separating the clusters. Yeah. So here in regression, you do not have, you don't have information on clusters, you just have data points. But in classification, you know the labels. This is like the positive cluster, this is the circular cluster. You have different clusters, and you want a line that separates the clusters, right? You want a line that is able to discriminate. So you can say this is separation or discrimination. So you're trying to discriminate between different classes. So maybe this is, for example, we looked at, maybe this is spam. So that's why you have a positive there, and this is not spam. So you get an email, and then you want to say, is the email falling here or is it falling here? This hyperplane is going to tell you that. If it is positive, then it's spam. If you pass the data through the hyperplane, it's negative, it's going to be here. So hyperplane is described by W transpose X, right? Let's say it's W transpose X equals 0. Any point here has W transpose X equals 0, right? On the hyperplane. But as soon as I move a little bit this side, the W transpose X is greater than 0. And as soon as I move a little bit this side, W transpose X is negative. But I need to know what W is. So what are you learning? You're learning W. In any classifier, what are you learning? You're learning this hyperplane. So once you learn a W, you give me an X. Okay, maybe your X is an email or X is an image. You pass W through X and say, is it positive or is it negative? If it's positive, I'm in this class. If it's negative, I'm in this class. So it's very simple in terms of what it's doing, right? Okay, so you can also look at classification as binary or multi-class. So binary is what we looked at, spam or not spam. So multi-class also we looked at, is it iris 1, iris 2, or iris 3. So there's multiple classes. It's not just 2. So you'll hear the word target. Target is just a label for the output. You're saying, is the target positive or negative? Positive means spam, negative means not spam. Or you can say the target is 0, 1, 2. So 0 could mean iris 1, 1 is iris 2, 2 is iris 3. So you have to take whatever your classes are and move it into something numerical or some kind of a number that denotes the class that you're trying to classify an image into. So maybe you do a mapping like this: iris 1, I map it to 0, iris 2, I map it to 1, and iris 3, I map it to 2. So then you're trying to predict 0, 1, or 2 for any image. It has to be between these 3. Yeah, I mean, some examples of how you would label, right? So let's say this is an email excerpt. could you please respond by tomorrow? You say, oh, that's not spam. So let's put a label -1. You get an email that looks like, congratulations, you've been selected for this offer, blah, blah, blah. You say, oh, that's spam. Then you say that's a label +1. And then you have something else looking for your presentation, not spam. So this could be part of your training data, right? So training data has something like this, some text and some label, text and some label. So someone is doing that for you. In the beginning, any email server would ask you to label it as spam or not spam. After a while, they figure it out. Now you don't have to label it because they're doing it for you. It's the same thing for images too. If you look at any of these social media websites, early on they would say, can you please tag the person here? And then you would tag. After a while, it tags it for you. So it's already taken that as training data and used it in a classification model or an image segmentation model. And it's figured out where to put the tags. And then now you see you upload a picture on Facebook and then it's already tagging it automatically. It's already learned the model. Okay, so the other concept with classification is the concept of linear separability. So linear separability refers to the idea that you can use a hyperplane to differentiate between two classes. I can use a hyperplane to say this is spam or this is not spam. Or I can use a linear hyperplane to say this is iris1 or iris2 or iris3. That's the assumption. So in linear separability, you can separate classes with a linear model. So this is a linear model. Why is it a linear model? Because it's a hyperplane, which is linear. That's why we call it a linear model. So when you hear things like this is a linear model, this is a non-linear model, in your mind, you should imagine a hyperplane or something that's not a hyperplane, that's non-linear. Here's an example of two classes that are non-linearly separable. Okay, so there are two concepts here. One is separability and one is linearity. This is linear and separable. This is separable but not linear because the separation is circular, it's not linear. Okay. You can have non-linear and non-separable. You can have linear and non-separable as well. So you can have all these combinations, right? Here's an example. This is linearly separable because a linear hyperplane can separate these circles from the positives, right? The negatives from the positives. That is almost linearly separable. So you can say this is a linear hyperplane, but it's not separable, exactly separable. But it's almost linearly separable. Why? Because most of the negatives are on one side and most of the positives on the other side, but there are a few positives on this side and a few negatives on the other side. So it's almost linearly separable. So most real world classifiers might fall in this category. You might never have a perfect separation. You might never perfectly say something is spam or not spam. You might still have that sneaky one email come into your spam folder when it's actually not spam. Right? So that's almost, and if you're using a linear model, if Gmail is using a linear model for spam classification, which they're not, then you would say it's almost linearly separable email classifier that's being used in your inbox. Does that make sense? Okay. All right, so let's move to in-class exercise, which is the following. Which of these following data sets is close to being linearly separable? Okay, so we don't have those data sets, so let's create them. 1, 2, 3, and 4. Okay, let's say Okay, this is one class. Let's look at the other class. Oh. And then we have all right. So let's say these are 4 data sets with 2 different classes, the cross and the circle. Is any of them completely linearly separable? The question is which is closest to being linearly separable. Okay, so what's your answer? Second one, right? Makes sense. Yeah, it's all, I mean, other ones are very deceptive. Like they look like you can have some separation, but then there's always something on the other side. So you can never really have, but this is really close. There's like 2 or 3 hanging in here, but you can almost linearly separate the negative and the positive class. So this is a good, so what does this tell us? So what's the point here? The point here is that this is a good candidate for a linear model, right? And conversely, you probably need to use a nonlinear model for this. For this, for this, and for this. There's no way a linear model can help you separate the classes for 1, 2, 3, 4. So this is a, here you can visualize it. In your real data sets, you may not be able to see all these classes nicely separated or not separated. But there are tests that can tell you, or you can fit a linear model, you get a bad error on your test set and you say, oh, I think a linear model is not good enough. I need something nonlinear. So let's also take a look at that. A nonlinear model, for instance, here might look something like this. Right? That means anything on this side is positive, anything on the other side is negative. So you may have to fit something like that. But you may have to use the nonlinear classifier to learn that kind of a function that discriminates the 2 classes. Here you can just like do this almost linearly separable. Maybe a little bit. Okay, so let's take a quick. Okay, so now that we've spoken about linear separability of classifier, let's actually look at a classifier. Like, how do you obtain this hyperplane? Like, what's a model that can use data, training data, and then give you something that looks like this? So you can actually discriminate between a positive or a negative class, right? Or even for multi-class classification, what you do. So here we'll look at logistic regression. It's a very good algorithm to know for classification. How many of us have looked at it before? So the word logistic comes from the word logit, which comes from the log of probability. Okay, so log of probability, logit, and then logistic. So this model involves taking log of probabilities of a data point being in the positive class or the negative class. That's why the word logistic regression. It's fairly intuitive. We already know that we want to identify a W such that points on this side of W are positive and points on this side of W are negative. So that's the goal. Learn this parameter W. Right? That's what we want to learn. So you can say that W transpose Xi is a score for the ith data point, right? So we can call this the score. So the score should be positive if it's a positive label, if Yi is plus 1. And the score should be negative if it's a negative label. Who decides positive and negative labels? You. So you can say spam is plus 1, you can also say spam is negative 1. But once you pick it, you have to be consistent with that. So you can put the spam in the positive class, and it makes sense. Spam is positive, right? You're looking for spam, spam is positive. Negative, there's no spam. So that's intuitive, so you can label it that way. But it doesn't matter, you can make spam negative and not spam positive. But that's your convention. So you decide, is the object that you care about positive class or negative class? So then you give these labels, right? So you want this model, logistic regression, to give you a positive score if it's plus 1, and a negative score if it's negative 1. Then it's able to perfectly classify every single data point. Or if it's not linearly separable, almost linearly separable, then you want the model to be in this scenario for most data points. For some data points, like, maybe here for this guy, you might still say it's positive class and it's actually negative. But for most of them, you're going to say it's positive and it's positive and negative and it's negative. That means you want the scores to be right for most of the data points. And you can have a few errors here and there. But you want that error to be as small as possible. So then there's a notion of probability in logistic regression. Like we said, logit refers to log of the probability. So it's also called log odds. What are the odds of something happening? So that's probability. Log of that, logistic. So the logistic function uses the sigmoid to come up with the probability. So the score, so if you look at W transpose X, what's the range for this for any given X? Let's say Xi. So this is fixed, but this is data point I. What can be the range for this? Yeah? Minus infinity to less infinity, right? The score itself doesn't have a bound, right? Like you say, it's an equation, right? It's a linear equation. Depending on your X and how it multiplies with W, you can go to the far left or you can go to the far right, or you can be somewhere in between. But that's not giving me a probability. So the sigmoid function is taking that score and converting it into a probability. So that's what you see here. It doesn't matter how far left you go, negative infinity, you're going to be at least 0. Or you might be exactly 0. Doesn't matter how far right you go, you're going to be at most 1 or exactly 1. Right? So what is this function? It is really simple. It's 1 over 1 plus e to the negative z. So if z is negative infinity, what do you get for this? 0. So so z is negative infinity, so this is going to be infinity. So 1 over infinity is 0. If z is plus infinity, what do you get? So z is plus infinity. This is 0, right? So 1 over 1 plus 0 is 1. So that's how this function is able to take a score that can be as large as you want or as small as you want and box it between 0 and 1. And as you know, a probability is something that's between 0 and 1. Any probability has to be between 0 and 1. So you say, okay, I think this email has a score of 100. Okay, what does that translate to in terms of probability? It's 0.9999 likely to be a spam. So you get a score, you get a probability of 0.9999 for that email, right? Or conversely, whatever. So depending on the score, you can then convert a probability. And then once you get a probability, you say, okay, I get a probability 0.7 that an email is spam. So should I call it a spam or not spam? Then you have a threshold. Maybe your threshold is 0.6. So your probability is above the threshold, so let's call it spam. The probability is below a threshold, let's call it not spam. So the default threshold is this, right, 0.5. But if you want to be more confident, you can say, well, something above this and something below this. So here I'm positive plus, here I'm negative plus. In between, I'm not sure. So usually when you set thresholds, you want to be confident. If you say something is 0.5 probability that it belongs to this class, it's also 0.5 probability that belongs to that class. So then you're not sure. You're 100% uncertain about the class, right? So that's not helpful. So usually you set a threshold and use a threshold to look at your probability and say, does it belong to the positive class or the negative class? So let's look at the design for logistic regression. So this is a design for it. So what's happening here? What is this? This is the input, right? X0 equals 1, x1, x2. These are also called, this is also called the feature vector. Right? X is x1, x2, xn. Feature vector. Feature vector is some representation of your data. You might have processed your data. For example, if you have an image, you might have done some processing on the image, done some convolutions, and those can fill in as x1, x2, x3, and so on. So x1 might be a convolution of this image with this kernel. And then you say x2 is something else. So you can take all of these features and put them together. So we want to differentiate raw data from features. So for example, in images are raw data. But you might not be using the pixel values as your x's. You might be processing it, maybe a convolution, maybe a TV, maybe smoothing, do something with it, and then you get your features, and that's what we call the feature vector. So that is your input. Now we're going to take the input and pass it through the weight vector. So this is the weight vector. So again, it's like W equals W1, W2. So notice there is a dummy variable here, x0 equals 1. That's usually because you want the hyperplane to be 0, W transpose x equals 0. So that intercept is included in the weights. So that's why this is a dummy input, x0 equals 1, so that you can say my hyperplane that discriminates the classes is W transpose x equals 0. So that x has a dummy x0. You can add it in. And this is what? This is a summation. So basically you're saying this is W transpose x. That's what it is. This fancy representation here is nothing but W transpose x. Take each element of x, multiply by W, and then sum it up, you get W transpose x. Okay, that's it. Nothing really fancy going on here. But the reason to represent it something like this is because this can be one small part of a neural network. A neural network is a bunch of these layers, like a bunch of these structures put together. Right? Okay, so we got a score. Now we pass the score through something, in this case a sigmoid. So we just described it, right? A score is from negative infinity to infinity. That doesn't give you a probability, so pass it through an activation function. So you hear activation function in neural networks. In this case, it's a sigmoid. Because the sigmoid converts a score to a probability, and that's what we're going to use to threshold and decide if it belongs to one class or the other. Okay, so our activation function is sigmoid, so that's 1 over 1 plus e to the negative c. So we just looked at that here. That's our activation function. And then you get your y. So here your y is something between, it's y is greater than 0 and y is 0. So y is a probability. So this is how you can represent logistic regression graphically. You take, and you know, it's very interesting. If you look at our brain, this is what's happening in our brain, but at a billion scale. Each of these could be a neuron. A neuron takes in an input, it aggregates the input, it does something to it, and then it passes it on. So right now, as you're listening to me, billions of neurons are firing in your brain, right? And doing this computation and passing chemical signals. so that you can understand what I'm saying, right? So it's happening all here right now, and yeah, and the learning that we do, like you've learned something, you're smart, means you've learned good W. Your W is in a good place, so you're able to understand what I'm saying, or I can understand how viewers. So our human brains, when we talk about learning, this is actually happening. It's happening through this kind of network, through the networks. Very fascinating. So yeah, a logistic regression, you can say, is a one-layer neural network. And in this course, we graduate from looking at logistic regression to a multi-layer neural network, a multi-layer convolutional neural network, which is more useful for domains, right? Because it is convolution, like we said, convolution is bread and butter. Images, it gets all the information. So you can start from one layer to multi-layer, and then again move from there to convolutional multi-layer neural network, and then you have something that can take an image and give you a text, or take an image and do something with it. So all the fancy things that we are looking at in computer vision is coming from some aggregation or putting together all these single neurons into multiple layers, and then kind of stacking them together in this way, and then training them, billions of parameters, and then you get a model that does some face recognition or zero to combination. But that's all coming up in the next week or so. So we're not there yet. So logistic regression. So as we said, the prediction is this is the probability. And then you have yi, which is true. So your true is either 0 or 1, okay? Or maybe negative 1. So you can use one of these dimensions. Your probability is going to be between 0 and 1. So this is discrete. It's 0 or 1, it's negative 1 or 1. But your y hat, which is the prediction, is probability, continues to be 0 or 1. And how do you match it? You threshold it. And then say, okay, now my threshold and y hat high, it's a 0 or it's a 1. Then you compare it with yi and hopefully you're predicting the right thing. But to do that, you need a loss function. A loss function is something that can guide your algorithm to learn how to predict the right way based on your data. So what is the loss function that's used by LR? It's the cross entropy. So this is something that you will see come up in many places. The cross entropy is a very useful loss function in homework, so look at it. So what is entropy? Entropy is given by the expression, but based on what you know, what would you say entropy measures? Measure of disorder, yeah. Measure of chaos. And for us, let's say measure of uncertainty. So entropy is a measure of uncertainty. So higher the entropy, higher the uncertainty. And lower the entropy, lower the uncertainty. Okay. So that's just entropy, right? So the definition of entropy, you take the probability distribution, let's say there's a probability distribution, and you sum up over each probability element of that negative pi log pi. So is this a positive or negative point? Negative point, how many think it's negative? How many think it's positive? Others think it's 0 because there are negative, positive, and negative. Okay. So it's a log. Okay, pi is positive because pi has to be 0. Log of pi, is that positive or negative?
Negative.
Negative because pi is between 0 and 1. So only if pi is greater than 1 will you have positive. So log of pi is negative. You know a negative sign there. So you're summing positive. non-negative integers, so it's the positive. This is very close. So your entropy of the probability distribution is always on. So due to invalid probability association. Oh, what happened? Okay, so entropy is a positive, non-negative quantity, right? So we're not interested in entropy as such, we're interested in cross entropy, which means looking at two probability distributions. In this case, is it true? What is it actually true? Is it +1, -1? And what are you predicting? Using any span or non-span. So there's two distributions going on. So if you can compare these two distributions, that's what cross entropy does. And you can optimize for it, you can minimize it. Then you will be able to run a model that for most classes, most data points, is able to predict the right class. Okay. So the binary cross entropy is a measure of distance between two binary probability distributions. Right? So let's say you have this is P, this is 1 by C, and then you have Q, and then 1 by C. Something like this, right? In binary. So it's span with probability P, not span with probability minus P, span with probability Q, not span with probability minus P. Okay. If it's a ground truth, P would usually be 1 or 0. This is span or not. But your prediction Q is going to be 0.8, 0.2, probably. So this quantity is comparing this and this. Okay. So it turns out if you minimize this probability, you're trying to make P as close to itself, or Q as close to itself for most data. Isn't that what you want? You want the distribution that you're predicting to match the truth. So that's why minimizing probability is a good thing to do for classification. And so it's a good loss function. Loss is basically measuring the difference between the two things. It's a good loss. Alright, so let's look at an entire exercise. It's probably not 1, it's 3. So based on your understanding of probability distributions, pick one that is actually. Right. Okay, what's your answer? 1 question. What do you think is question? Okay. Any other answer? Huh? The plus? Okay. Any other answer? Okay, so it's uniform. Why uniform? Because there's complete uncertainty on probability. Uniform gives the same probability every possible time. So you have no idea what's going on. It's all chaos. Right? I mean, I think it helps if you draw a picture. The draw shape looks like this, right? The draw shape like this. Uniform looks like this. You see, it doesn't matter where you are. It's giving you the same value. It's not preferring any particular value. There's complete chaos. Right? Maximum uncertainty. Maximum uncertainty means maximum uncertainty. So uniform distribution, you can also show it mathematically that it has a maximum. I mean, how do you show it? I mean, it's actually not too hard. Correct. So entropy of distribution is summation by PI log here. So this is the kind of a concave function. So if I take the gradient of this and say it's 0, then the P that satisfies that equation will be the maximum distribution. Right? This is concave. This gradient is 0 at the top. So if you find the one that sets the gradient to 0, that's the top, which is the maximum. So if you do that, you get minus PI minus 1 plus PI equals 0. So that means all PI is a constant. So log here is constant, it's uniform. Right? Because it doesn't matter where the I is, it's the same thing. So that's why you have to that's binomial, I mean, it's again the same story. Binomial is discrete. We are comparing, not exactly comparing numbers to others, but binomial minus that, but again, it's not uniform. All right. So we'll cover this and then we'll stop for the day. There's more to cover, but let's look at the cross entropy as a loss function. So this is what is it? This is the truth, right? Either you're on this class or that class. Finally, what is this? This is your prediction. It's between 0 and unknown. So this cross entropy is trying to minimize the. So this is you're finding W that minimizes the summation for all possible data points, or as we define by as. Where is W coming in this picture? I don't see a W. Sorry? Yeah, y hat I is 1 over 1 plus super negative W transpose. So y hat is a function of W. So when you minimize this, you're optimizing for W in necessity inside. But you have to minimize it across all your average. On an average, pick a W that gives me the least error on binary cross entropy across all the data points. So then I would have identified something that's as close to y as possible for all data points. Yeah, so minimizing the LR loss, so this minimize the LR loss option and compare. Okay. Most stuff. Yeah, I think we'll stop here for the day. There's more. Okay. So for now, we can just say that we understand why. We probably understand why binary cross entropy is good loss function, but also get a little bit more detail next lecture. And then finish binary classification. Your assignment in 3. Let's stop here.